Greetings. Welcome to our second presentation on concrete, where we're going to be focusing specifically on different components that make up structural concrete systems. We're going to talk about foundation settlement. We're going to talk about a couple different design and construction defects, different foundation types, as well as how foundations are depicted on structural drawings. So, in general, this is a nice drawing, probably from a Ching book. So foundations, they are there to transmit building loads to the rock or soil below them. So the weight of the building itself, the weight of the occupants, the weight of any environmental loads such as rain or snow, wind, lateral loads coming in, ground pressure and wind. The building has to transfer all of that weight, all of those forces down into the earth below. The foundation must not fail, because then the building would collapse, and that would, of course, not acceptable. Must not settle, because if they settle, they do damage the structure and the interior, the entire building. They must be economically, technically, and practically feasible, with no adverse effects to the surrounding area. So some basic things that we look for in foundations. Okay, settlement, foundation settlement. Get that a little smaller there. So we have two different types here. We see uniform settlement and differential settlement here. A stable building, there is no settlement. That is what we work towards, of course. Uniform settlement, so there's it could disrupt building services or damage elements like stairs and walks at the building site and interface. So that is here where the entire building has settled uniformly, or all pieces sank together. But there could be problems, of course, at where the building meets the earth, of course. That could definitely cause some problems. More damaging than that is typically differential settlement. So damages to finishes, cladding, and other components become distorted when things don't settle together. So this is probably more common and probably more damaging. And here we see, again, some more visuals here. So uniform settling, the whole house settled together. Tipping, often without cracking. So the earth settled kind of, I guess, neatly enough so that part of it didn't just sink. And that's what we see here, differential settlement. So that this is probably the most common here. Where just a portion, like a corner, gets washed out because of poor water drainage, for instance, and the earth underneath the footing gets washed out, and then the footing cracks, settles, and the rest of the house follows. That's probably the most common scenario there. And that's what we see happening here. So soil settlement, if some of the soil beneath the foundation wall compresses or gets washed away. So plumbing leaks could do it, poor drainage systems could do it. Not very uncommon. Soil pressure coming in from the outside. So outside the foundation, expansive clay soils or water-saturated soils really push on the foundation. That's what we see here is a bowing wall. If this pressure is too great for the wall, so then horizontal or diagonal cracks will most likely develop. They're often accompanied by wall displacement in the form of bowing or tilting. So this is an image of expansive clay soil. When it gets wet, it literally expands a lot. And so here we see the water-saturated earth, creating a lot more weight pushing on that. And then here, this is kind of a graphic studying a wall that has been damaged or displaced. So it looks like they struck a plumb line right there, that black line, and this is showing just how far the wall is bowing out of plane. So 4 inches at the bottom and 3 1/4 inches at the top. So that is a very significant, a lot of movement in that wall. That is dangerous. Okay, design and construction defects. So inadequate reinforcement, weak concrete, undersized footings are some of the construction defects that make a foundation wall more prone to cracking. So all of these things, they're saying construction defects, but these are really all design defects. If the designer specified reinforcement that is under reinforced, and that's of course the designer's issue. If they put in the wrong, if the contractors put in the wrong reinforcement, that's another issue. Same with concrete. Was the proper concrete specified, and was the proper concrete installed and placed. So this is an issue that could sit on either side of the design or construction fence. Footings, that typically belongs to the designer. Usually contractors are following the plans to build the proper size footings at least. So I think if there were undersized footings, that issue would belong to the designer, hopefully, and not the contractor. All right, so in general, foundations need to reach below the frost line. Very important, okay? So the depth to which groundwater in soil is expected to freeze. Okay, so depending on the climatic conditions in the area, heat transfer properties in the very, very local area, the very small area. So the township that you live in, what part of the state you live in, all affects the frost line, but also the immediate area right around the house could affect it. Could affect where exactly where exactly things are freezing or not freezing. But the frost line in general is something set by building codes. So to take into account frost heaving that could damage buildings. So we want to get our foundations need to be down below that. Building codes usually require that the bottom of the footing must be below the frost line, not the top. Okay. And this is a typical map. So here in Philadelphia, where I am, the frost depth is about 36 inches. So that's for any foundations have to be at least down that far, be it a simple deck or a porch or a house. It has to be at least 36 feet, 36 inches down. So here we could see it getting up to 72 inches. So that's a lot of digging. 6 feet you'd have to dig up in this area. So very deep. Along the water, it's only 6 inches, 6 inches. So this is where slab-on-grade construction is permitted, down in the most southern part of the United States, obviously, where up in the most northern part, they're digging very substantial foundations. Even for the simple deck, again, digging down 6 feet. Okay, foundation types. So broad classifications. There are shallow foundations and deep foundations. So transfer loads to the earth close to the base of the structure, less expensive than deep foundations, and typically used whenever possible. So here we see the same mid-rise with two different foundation types. Shallow, again, getting however far below the earth it needs to get for the purpose of getting down below the frost line. Here, they wanted to dig down, probably get a whole story down there, because there's probably a limit for mid-rises in terms of how high they could grow. So perhaps they chose to pay the money to dig a whole foundation, bury a whole story down there under the ground. Deep foundations extend down through weak or unstable earth to reach more competent soil. So this is not an issue of frost. This is an issue of finding proper footing down there. So inadequate soil have to get down to the bedrock is one way to do it. There are different types of foundations that could address unstable soil in different ways, but given probably the geotechnical study of this area, this is what the engineer thought would be the most cost-effective way to do it, was to dig piles down that deep. So that's what that all says. And then often the choice is obvious, but in some cases, in-depth investigations and evaluations have to be maybe required to think about the cost, basically, of the different strategies. Okay, so the term footing is used in conjunction with shallow foundations commonly. A footing is a foundation unit constructed of brick, masonry, or concrete underneath the wall or column for the purpose of distributing the load over a large area. Reinforced concrete and mesh and steel is embedded to give it tensile strength. So we're talking about these concrete pieces down here. All that weight from the building comes down and then it gets distributed over a broader area, kind of like these snowshoes. So often if you're walking without your snowshoes, then your foot could kind of be a concentrated point load and will break the snow. But here, probably in addition to speed and other things that I'm unaware of, but in general, one purpose is definitely to spread out the person's weight so that the weight is distributed over a greater area. And that's exactly what footings do. Okay, and then how they take place. So again, down in the southern parts of America here, we could just do simple slab on grade, reaching down 6 inches. Here's a crawl space, so that is coming down, whatever it is, 2 feet or so perhaps. And then it provides access to the underside of the structure. So maybe putting heating and air conditioning, for instance, down there could be a good thing. Plumbing could be down there. And then a full basement. So slab, crawl space, and what is going to be a partial basement at least. It's at full grade in the back, and looks like grade might be dropping as we move to the front. Column footings, so simple, sloped, stepped. Strip wall footings. And then we can see it going in there. So there's our column footing, and there's the form for the columns. So done in several pours, so the rebar is all in place, and then we can see partial pours going on. Here's our wall, our strip across the bottom. We see the strip down there, and then here we see it in section. So strip footing, rebar, hooks here embedded in the footing. That's what we see here in the picture. They don't belong together, but not coincidentally, I'd still say. And then it comes up, and then there's another concrete stem wall there. And so these two are tied together with that rebar. Spread footings, also called isolated or pad footings, reaching to columns. So here's the single footing in section, and then looking down at the top view in plan. So here we have a step footing again, kind of looking like a pyramid from the top. And here's actually something more pyramidal, where we have sloped sides. So sometimes you could run them continuously, or sometimes they're standalone. And step footings to follow the frost line and not dig down any deeper than necessary. And then what these often look like in plans for all projects, despite the scale, is typically how they're depicted. So footings are typically always drawn as dashed lines. So we're down here in we call it the foundation plan. So we see the foundation walls, however high they are, doesn't seem to be indicated right here. So this is the footing sizes. So again, those are the dashed lines. So we have wider footings. We don't see that. We see that right here, right? So we're looking down at this wall, which is, we'd have to do a little math to figure out exactly how wide that wall is. I don't see it right there. Probably 8, whatever it is. We see the wall solid, and then we see the dashed lines of the footing, which is wider below. So let's circle back there. So there's our dark wall, dashed lines for the footing. Footing schedule, so house walls, deck and porches, bearing walls, and garage walls. So as long as they're pointing out the bearing walls here, that could work, I guess. But some of these are shared also. So like, does this wall belong to the garage or to the house? That's a little peculiar. Maybe a little oversimplified there. But that's what they look like. And so here's a nice clear plan. So here we have some square pad footings, isolated footings, and then it looks like the dashed line here could be a beam, perhaps, connecting the two under the earth down near the footing. I see something down there. And then we cut through at our columns. So our columns are dark, and the footings down below are all dashed. And this one's drawn well too. So here we see our dark columns, walls connecting them, and these would be our pads. Okay, thank you.